In this video, I want to discuss where the field is moving towards in terms of working with imbalanced datasets. And I want to address that up front so we know what to expect throughout the rest of the course. Now, if you worked with imbalanced datasets already, you probably heard about SMOTE. SMOTE is an algorithm that creates observations. It creates synthetic data that look like those observations from the minority class. And the idea says that if we enrich the dataset with observations that look like the minority class, then we are helping the machine learning models discriminate between minority and majority, and therefore we are helping improve the performance of the machine learning model. Now, the idea is sound, but if you look at how SMOTE works, I think you begin to see that this model is applicable only to a very small number of situations. And in my opinion, there has been a little bit of an overhype about the applicability and the benefits that these models bring to training machine learning models on imbalanced datasets. Now, overhyping ideas or algorithms in data science is not unusual. There's been an overhype about SMOTE. There has also been an overhype about SHAP for interpretability. And if you ask me, there's also a little bit of an overhype when it comes to large language models. But leaving my opinion aside, if you follow data science communities, you probably also started to see discussions that ask why SMOTE is not used in prize-winning Kaggle solutions, or if oversampling or undersampling a dataset will cause issues in the use of the machine learning models. And several of us have actually tried SMOTE in our projects, and we didn't actually see this promised improvement in the performance. And if you're active on social, you probably also started to see some threads and discussions asking for examples where SMOTE has actually helped in real-world scenarios. So we have a lot of publications and articles that say that SMOTE improved the performance of the model, and then we have our experience and discussions that we find online saying that actually SMOTE doesn't work. So where do we stand? Well, a few years ago, an article came up which was the first systematic review of the usability and the benefits of using SMOTE with imbalanced datasets. So these guys evaluated whether SMOTE improves the performance of various machine learning models across various datasets, optimizing various metrics. So to me, this is the first systematic approach that tries to answer the question of whether SMOTE works or it does not. And the first thing that came out of this article is that most of the articles that discuss SMOTE or any of the variants of SMOTE used weak learners like decision trees, random forests, AdaBoost, support vector machines, and multi-layer perceptrons. And not only they used weak learners, but they optimized metrics that require a threshold, like the precision and the recall. And this threshold, which is the value of the probability at which we assign an observation to one class, say the probability of 1, is set at 0.5. So if the probability is bigger than 5, then we would say that this is class 1, which is in general the minority class. Otherwise, it would belong to the minority class. And this is actually a very bad design because a probability threshold of 0.5 is only useful at best in balanced datasets. But when we work with imbalanced datasets, we usually set the thresholds at different values, and we will modify the threshold depending on whether we want to get more or less false positives or false negatives. So using a threshold of 0.5 is not actually suitable for imbalanced datasets. And then we are testing an algorithm like SMOTE on the performance improvement of a model that is trained to optimize a metric that is not properly set. Now, I thought that it was quite obvious that we should not use 0.5, but it turns out that apparently using a threshold that cuts at 0.5 is quite widespread even if we're working with imbalanced datasets. So I guess this is one of the lessons to take home right from the beginning. If we're working with imbalanced datasets and our metrics require a threshold, we should not use 0.5, we should find the optimal threshold. But coming back to this article that makes a systematic assessment of the benefits of SMOTE, what these guys did is they tested whether SMOTE improved the performance of several machine learning models, including all the ones that have already been studied, like decision trees, AdaBoost, support vector machines, and also they included strong gradient boosting machine models like XGBoost, CatBoost, and LightGBMs. And they evaluated the performance of these models with or without using SMOTE, but also evaluating several error metrics. Those that depend on a continuous value of the probability, like the log loss or the ROC under the curve, and also error metrics like the precision and recall. And for these error metrics, they evaluated the performance of the models with or without adjusting the threshold. And what they found is, first, that XGBoost, CatBoost, and LightGBMs outperform all other models. I mean, there is no surprise here, we knew this already. But when using these machine learning models, then they found that using SMOTE did not improve the performance of these GBMs. So if we're training XGBoost or CatBoost on an imbalanced dataset, then using SMOTE doesn't really make a difference. And this is probably why many of us say that SMOTE don't work. I guess most of us are using gradient boosted machines. For sure, the people that compete on Kaggle are competing with these strong classifiers. Now, what happened when they tried SMOTE on weak learners? What they saw is that SMOTE actually did improve the performance of weak learners when evaluating metrics that depend on probability, like the ROC-AUC or the log loss. So using SMOTE with weak learners and these types of metrics does seem to improve the performance of the classifier overall on the entire spectrum of probabilities. Now they then evaluated the improvement that SMOTE brings on all these classifiers when they use a cutoff of 0.5 and evaluate metrics like precision, recall, false positive, and false negatives. And what they saw is that SMOTE improved the performance of all classifiers when the threshold was arbitrarily set at 0.5. But here is the interesting bit. When they optimized the threshold, so when they changed the threshold for each particular dataset and model so that it returns the best value of the metric possible, then the improvement caused by SMOTE was lost. So what this tells us is that actually, if we were not to set the probability threshold cut at 0.5, if we were to optimize the threshold, then we actually don't need to use SMOTE. And this is sort of a revolution. I was being ironic there. There was another article a little bit before the one that we just discussed that said that we should stop oversampling for class imbalance. And they evaluated SMOTE and other algorithms on 3 datasets. And what they saw here is that the synthetic data created by SMOTE are not representative of the real data. So what they are telling us is that when we use SMOTE to create synthetic data that in theory should look like the minority class, what's happening is that we are not creating synthetic data that is possible to exist in a real-life situation. And they argue that that makes SMOTE not suitable when we want to use the machine learning models in real-life scenarios. And finally, to wrap up the new discoveries in terms of working with imbalanced datasets and the use of sampling, there was another article this year in 2024 that says that using rebalancing techniques, so either under or oversampling, in particular algorithms related to SMOTE, harm machine learning-based prediction models in the sense that they irreversibly affect the classifier calibration. And we have a dedicated section talking about classifier calibration, but calibration per se is not paramount for performance, so we can have a model that performs very well even if it is not calibrated. The problem is that not having a calibrated classifier can make this classifier hard to use for our stakeholders. The users of these models understand or tend to think about probabilities like the real risk of something occurring. So like if, for example, if we are detecting fraud and the model returns 0.8, the user of that model, who may not be a machine learning expert, tends to think that this 0.8 means that 8 out of 10 observations in the similar circumstances will be fraudulent. And if the classifier is not calibrated, then that's not the case. So using models, using algorithms that destroy the classifier calibration, even if they return a performant classifier, this classifier may not be useful because the stakeholders cannot really make sense of it. So, where does this leave us? Should we use SMOTE? Should we use resampling or not? These are very general, high-level guidelines, which basically suggest that if you're using strong gradient-boosted machines like XGBoost or CatBoost, most likely SMOTE will not improve the model performance. And this is what I've seen in my experience, and this is what Kaggle winners tell us. But there's been a lot of evidence, and this article that did the systematic review also confirmed SMOTE can improve the performance of some weak learners, and in particular, SMOTE can be useful to improve the performance of models that do not actually output probabilities, like for example the support vector machine of sklearn, which only returns the class. So in those situations where we don't have probabilities and we cannot play with the threshold, then SMOTE can help improve the model performance. So how should we approach working with imbalanced datasets? Well, as a rule of thumb, whenever possible, let's try and use strong gradient-boosted machines like XGBoost or CatBoost. The second step is that we should adjust the probability threshold when we are evaluating models that depend on the threshold and not fall back to the default 0.5 that it was up to very recently hard-coded in scikit-learn. Scikit-learn now also has a class that allows us to optimize the threshold as we train the model, and we're going to discuss that later in the class as well. Another thing that is important is that we should use, or at least we should evaluate more than one model performance metric, because resampling, being undersampling or oversampling, has been shown to improve the values of some metrics, but actually deteriorate the values of others. So we're not getting a complete view of what's going on with this classifier if we only evaluate one metric. If we're using oversampling algorithms, in particular if we are creating synthetic data points, I think this goes without saying, but we should explore the result of our data manipulation. So these synthetic data points that are being created, do they look like the minority class, and are they actually possible given the characteristics of my data? And if they are not possible, then we should probably not use that approach. And finally, it's also good practice to check the calibration of our classifiers. We're going to talk about all of this throughout the class. In the first section, we're going to talk about metrics and how to set up the threshold. Then we're going to talk about cost-sensitive learning, which is a way of introducing cost in the training of the machine learning algorithms without the need of resampling. And after that, we're going to discuss resampling methods, understand very well the characteristics of this method, so we're able to say when we can use them and when we should better leave them behind. And after that, we're going to learn how to evaluate if our classifiers are calibrated, and if they are not, how we can calibrate them. So with this, let's jump straight away into the contents of the course. See you there.